Hello, so in this video we're going to be looking at applying our knowledge of vectors to solve, I guess, more geometric or harder, I guess, problems. So stuff involving shapes and stuff like that. So we won't really learn anything new, but we will be applying stuff. And it is a very good idea to still watch the video, right? And to look at the problems and the questions we do. Especially because I would say this is probably one of the hardest topics, at least at AS, that students find difficult. Uh, Geometric problems with vectors. So hopefully after this video will give people some confidence to to tackle these sort of questions. Right. Okay. And again, like when I did the methods of proof video, so chapter 7.5, I split it into three sort of distinct subtopics. I'm going to do the same here because there's like three certain types of questions that things fall into, three different mini topics that things fall into. So obviously I will split it, the video, I will timestamp it into those three sections so you can look at either one, okay? So first of all then, before we jump into it, I do need to cover one thing that I haven't covered yet. And that is the idea of 3 points on a straight line. Okay, so for example, if I had a point A here, and a point B here, and say a point C there, all on a straight line, right? All 3 points on a straight line. And more specifically, they're on a vector, right? So this line, but it's a vector, right? Now, these 3 points on the same line are on the same vector or the same straight line, right? You can see that, but sometimes we need to give a sort of mathematical definition for what it means to be on the straight line. We can see it, but sometimes we can't see it, right? We might just be given the vectors, right? So how do we show that these are, say if we got the so say if we have like the position vectors of A, B and C, so sort of the coordinates, right? How do we know all three of them? How can we show all three of them are on the straight line? Well, consider this then. So A to B, right? A to B is that part there. So I've just extracted that part of the vector, right? That part of the line from A to B only. Now I'm going to do the same for A, but now I'm going to do the whole lot. Well, the whole line up to C, right? Ooh. There, right? And then B would be somewhere in the middle again, roughly. Just how I've drawn it. So now I've got these two parts of the straight line right over here, okay? But you can see, what do you notice with these two sort of vectors right over here? What do you notice? So hopefully you notice that basically, obviously the length is going to be different, but the direction and sort of the gradient is the same, okay? So what that means is then we can say that 3 points then have to be on a straight line if obviously we can create, if we can just chop up the line, right, into different lines from just 2 points, right? From A to B, or from A to C, or even from B to C, right? We can even do B to C, right? Cool. There, right? Hopefully you notice all three lines, no matter how, if I just cherry pick or just cut the main line here into just the line between two of the points, all of them have the same gradient, right? Which means in vector terms they're parallel, right? So if I just take any 2 points from the straight line, right, instead of 3, in this way, that they're going to be parallel. They're going to have the same direction. They're going to have the same uh, vector, the same direction, right? So they'll all be parallel, no matter what line, right, we sort of make from this by just taking 2 points instead. Obviously the directions are all going to be different, as you can see here, but they're all the same gradient, so they're all sort of the same direction, so they're all parallel, which means if we have 3 points, A, B, C, they lie on the straight line. They lie on the same straight line, or the same line. That's if we have 3 points, they lie on the same line. If they're vectors, then if the vectors between two of these points which means we could either have the vector AB, which is going to be that vector there, or we could have A to C, or we could have B to C, right? So just the vector between any 2 points on this line, they're parallel, right? Or parallel, right? And that means then that they're multiples of each other, right? Because remember, parallel vectors, they're both parallel if they're multiples of one another. Okay. And there we are, right? So we have so if you have any 3 points, right, we need to show that they're all on the straight line, or all on the same line. Then if we find vectors between, if we find 2 vectors, right, between any 2 vectors, so between A to B, or from A to C, or from B to C, right? So any combination of 2 points, and if 2 vectors of those are parallel, then they must all be on the same straight line, right? Okay. Okay, so we're gonna start looking at questions like this then, and these are actually GCSE questions, but the more like the very higher end, at like the grade 8, 9 sort of areas. So again, they can be quite tricky. Even at A level, these questions can be tricky. But let's have a look at it. Okay, so I'm told in the diagram here, the points A and B have position vectors bold A and bold B. So they've drawn that on the diagram for us, right? And we're also told that the point P divides AB in the ratio 1 to 2. Right, so that means P there, if it divides AB in the ratio 1 to 2, then it's saying that the first part from A to P is going to be one part. And then from P to B, the other part of the line is going to be the remaining 2 parts, right? So I'll just say it as this, so 1 to 2, right? I've just labelled it there. But obviously the whole line then is going to be AB. AB is going to be all 3 parts, obviously, because then if you add the 1 and the 2, you get 3. Okay. And so AB will be there. Okay. We need to find the position vector of P. Now, position vector of P, again, remember last time, position vector is essentially the coordinate, or you can think of it as from the origin to the point, okay? So if you want the position vector of P, it's from the origin, so O to P, okay? That's what we want to find, okay? So that's going to be that vector there, then it's going to be O to P. So obviously we can't go directly. So a very common theme then is we need to find another way using the information we've got. Well, actually, we can go from O to A then, and then A to P, right? And then see what we can do. Okay. So now OA then, OA we're given is A, the vector A. Then A to P, well, we know, well, we don't know AP, but we do know, because we're given it, AP is one part out of 3 parts of AB. So it's going to be a third of AB, right? The vector AB. Okay, now then that's going to be A. Now what about, how do we find AB then? We're actually not given AB either, right? Really, we're not given the vector AB. They're not told us what the vector AB is. Only what the vector A and B are, A and B, but not A to B. Okay, we're only given the position vectors of A to B. So then this is why I say this little hint up here. We are told we're told that geometric vectors, when you're finding the vector, in this case O to P, right, we want to find O to P, but in this case we also then need to find AB, which we're also not given. So we need to find the vector for AB. and then work our way to OP. So we might need to find a vector and a vector, okay? So we need to sort of apply the same sort of logic then to find AB. Well, AB then, obviously we can't go from A to B directly because we don't have the information for it. But we do know we can go the other way around the triangle. Instead of from A to B, right, that way, we can go from A to O, then O to B, okay? So then that's going to be a third of, well, A to O is going to be the reverse of OA, so it's going to be minus OA, add O to B, okay? Then that's A, add a third. Now minus OA, that's going to be minus the vector A, so minus A, and OB is the vector B. And so then if we sort of expand that, then we're going to get A, add minus a third of A, add a third of B. And so lastly, if we just collect the A's, A minus a third A is 2/3 A, add a third B. And that is my vector O to P, or in other words, the position vector of P, okay, because it's from the origin O. And there we are. So again, sort of a more simpler example. We're going to look at more complicated ones now in a second. But I want to demonstrate, I just want to hone in on what I've said up here, that we might often need to find a vector in order to find another one. Okay, so in this case, we wanted to find OP, but we needed AB as well. So we needed to find that vector. Okay, so yeah. Okay. Okay, now we got this question then. Okay. And I'm said up here now that additionally now we can solve vector problems like this, right, by finding two different paths for the same vector, and then we can use simultaneous equations. More on that as we work through the example. But the main idea is we might need to also find two different ways of getting to the same vector, or two different paths that start and end at the same point. We'll see what that means in a sec. But let's have a look at the question. We are told that OABC is a parallelogram, and P is the point where the diagonals O to B and A to C intersect there. We're told that the vectors A and bold C are equal to O to A and O to C, so we can add that on, right? So O to A is going to be there, and O to C is going to be there. Now actually, because it's a parallelogram, then that means the opposite sides will have the same vector, so the parallel, right? The opposite sides are parallel, so this means A to B is going to be C, and C to B is going to be A as well. We can add that on. Right, now we're told, that's really it, that's all we're told really. Prove that the diagonals bisect each other, which basically means they intersect at the midpoint. We can kind of see that here, right? So the diagonal OB, right, is there. We can see that P is kind of halfway on OB, and likewise the diagonal A to C, we can see it's halfway kind of to P. So visually it makes sense, but obviously we need to prove it mathematically, right? So we need to show that they both intersect at the midpoint on the lines, right? So how on earth are we going to do that then? Right. Well, actually, this is gonna use the idea about the straight line stuff we talked about at the start of this. So firstly, if it's talking about the diagonals, it's probably best to consider the vectors of the diagonals, right? So firstly, well, let's find the position vector of P, right? Let's find the vector P. That would be OP then, right? I think that would be a good start, because then if we find P, we might be able to do something, okay? Now, to go from O to P, right, that vector there from O to P, we don't know anything about it, right? So we need to find a different way and get it from O to P. Well, firstly, we can consider the fact it's on the diagonal O to B, right? So actually, if I sort of draw the line out from O to P to B, hopefully you can see they're on the same line, which means if I then have the vector O to P, if I just take the vector O to P then, so the line from O to P, that again is going to be the same sort of direction as the whole line O to B, right? The vector O to B then is going to be parallel to O to P because they're both the same direction. So we could say then, because O to B, right, I'll make a note, O to B is parallel to O to P as they're on the straight line, as OPB on the same line, so they're on the same diagonal, right? And hopefully you can see, because of my diagram of drawing the lines out, you can see that they're going to be parallel vectors, O to B and O to P. Then that means we can say again, because what a parallel vector means, they're multiples of one another, then OP is going to be some K, lots of OB, right? Because O to P is parallel to OB, so they're multiples of each other. Right, so then we need to find a vector for OB, right? So it's going to be K lots of, and then how are we going to get from O to B then? Well, actually, we can go along the parallelogram. So if we start at O and we want to end at B, from O to B, right? We can go from O to A and then A to B, right? We should then be the vector A add B, add C, right? And so there we are. So if we expand that out, it's going to be K lots of A add K lots of C, okay? So multiple K. Now, obviously, we don't know what K is. It's just a multiple. But this is where my hint is going to come into play here with these sort of questions, because I want to find two different paths for the same vector. In other words, I want to find another way of finding O to P, right? So an alternative path for from O to P, right? For that vector there. So so I considered firstly the fact it's on the diagonal O to B, right? So I've used the fact it's on the diagonal O to B. Now I need to use the fact it's going to be on the diagonal A to C, right? The other diagonal. So let's consider that instead. So how are we going to get on the diagonal A to C? Well, actually, if we're starting at O and ending at P, we can go from O to A and then A to P, right? And we're going to then apply the same sort of logic because it's on the same straight line. So we're going to go from O to A, then A to P. Well, O to A, again, is just the vector A. And then A to P. Now, A to P, right, the vector A to P, again, hopefully you notice A, P and C are on the same straight line. So that means A to P then, the vector 8 from A to P, is going to then be parallel to A to C, okay? So that means A to P is going to be some multiple T, say, lots of the vector A to C, okay? Because again, if I draw it out, if I have the point A, the point B, the point P, and the point C, they're all on the same line. They're on the same diagonal. So any vector you can make between these points are going to be all parallel. So the vector from A to P is going to be parallel as the vector from A to C because they're all on the same line, the same gradient, if you will. So they're the same direction, they're parallel, okay? So the vector from A to P has to be a multiple of A to C because they're both parallel to each other. So then I can sort of substitute that in. So then it's going to be add T, lots of AC. And then again, I need to find a way of getting A to C then, right? So then that's going to be well, forget if we want to start at A and end at C then to find A to C. Well, actually we can go from A to if we can go along the parallelogram, we can go from A to B and then B to C, right? So A to B, T, oh that's a T there. There we are, T lots of AB, add BC. Okay, but then A to B then. Okay, well A to B here is the vector C, right? I've drawn that on. The vector AB is C. The T lots of vector C. and then from B to C, so from B to C then, well, C to B is A, right? Remember, the direction of the arrow or the vector is important. Because the arrow is facing up, the arrowhead is facing upwards, it's going from C to B, right? But I want to go from B to C instead, the other way. So it's going to be negative the vector A then, right? So negative A to reverse the direction. And so then if we expand it then, well, we're going to get A minus T lots of A, add T lots of C. Well, actually then, we found, now we're actually heading somewhere, because now we have two different expressions for O to P. This expression, right, I'll call that expression 1, and this expression for OP, another expression, but they're the same vector. They're the same vector for O to P. So that means they both have to be equal, right? So therefore, I can say that, well, 1 equals 2. So that means Ka add Kc is equal to A minus T lots of A, add T lots of C. And there we are. Now, at this point forward, we can then create some simultaneous equations by doing something called comparing coefficients, meaning the coefficients of each vector have to be the same if they're equal, which means the A part of both sides has to be the same. So does the C part, right? So that means we get these two equations. So that means Ka is going to equal A minus T lots of A if we compare the A parts. But actually then, if we compare the coefficients, we can say that therefore K is going to be 1A, so that's going to be 1 minus T, okay? We can also then do the same for the C vector. So Kc is then also going to equal, well, Tc. Well, that is a plus T there. There we are, so Tc. So therefore K equals T. Well, actually then we got these simultaneous equations. I'll call them equation 3 and 4, although you don't really need to, really. But then if K equals T, then I can say that therefore I can substitute that into the top equation, right? So if K equals T, then T equals 1 minus T, right? So then I can add them to get 2. I can add T to both sides to get 2T is 1. So then T is a half. And there we are. So then, therefore, K also equals a half because K is equal to T. And there we are. Okay, so now we've got these K and T values. Well, actually, let's go back to the question then. We need to show that the diagonals bisect. Well, the diagonals, remember, are OB and AC, right? They're the diagonals on my parallelogram. Well, actually, then if we go back to our working, firstly for this first part here, well, actually, we said that OP is K lots of OP is K lots of OB. But we know what K is, so then that means K is a half, so that means OP is a half OB, right? We also said that here, that A to P is T lots of AC. So then AP is, we know that T is a half as well, so AP is going to be half AC. Okay. Now why is this important? Well, actually, hopefully, you can see that the half kind of signifies it's going to be a midpoint because it's halfway, right? So that's kind of the idea. So we kind of proved it really now because we've shown that the vector from A to P, right? A to P there, that is a half of A to C. Well, that's exactly, that means then that P has to be halfway on AC. And we've also shown that for the diagonal O to B, that P, again, from O to P, that's a half. So then that means P to B has to be a half as well, the other remainder of OB. So A to P is a half, and then that has to be a half. So P has to be midway through on both lines, right? Right, so because so remember that OB and AC are the diagonals, and we've shown that that P on the line is halfway through on the lines. So therefore P is the midpoint of OB, of diagonals I should say, OB and AC. And there we are. So it bisects it, right? So what does it say? The diagonals must bisect each other. So diagonals must bisect each other. Because obviously they're going to intersect at P, and P's the midpoint. So they're both halfway at P. Okay. And there we are. Quite a harsh question that is. Harsh question. But hopefully you sort of understood the logic behind that now, of how we can find two different ways of getting the same vector. So the whole idea of this question is to find a vector for P on each diagonal. So the first one I considered the vector OB, because that's the first diagonal. Then a vector for AC for the second one. And then I've got two different expressions for OP. And then I found that. I found the values of T and K. And then I deduced that on P, that P is basically halfway on each diagonal. Okay, I got this half here, which means it has to be a midpoint because it's halfway. And so there we are. Alright, so now we've got this question then. Again, we're going to be looking at comparing coefficients again. So we're told that firstly, so we're told in this question that OPQ is a triangle. We're told that two lots of PR is RQ. Now actually, let me draw this diagram because it's a little bit small. If I draw it a bit bigger, yeah. So Q would be Q there. Then we're going to have O. Then we're going to have O, the origin. Then we're going to have P. Then we're going to have, but then we're going to have, well actually, then we're going to go from O to S. Then we're going to have P to R, there. Then we're going to have R to Q. Okay, so that's my diagram. Okay, I just thought I'd make it a bit bigger to be clear. So that's the vector B, and that's the vector A. That's all given to me. Now I'm told that this is a triangle, and two lots of PR is vector PR is RQ. So this is talking about the vector P to R, which is that part, and then R to Q, so that part, right? So R to P, the P to R, that vector there, is going to be two lots of PR is RQ, right? So that means RQ is two lots of PR. So it's going to be double the amount from P to R. So if P to R then is going to be, say, one part, then that means R to Q is going to be two parts, right? So I'll label that 1 and 2, okay? We're also told that three lots of OR is OS. So in other words, OS then is going to be three lots of O to R. So the vector O to R is there. So that's going to be one part. If I extend this line then, there we are at S, then hopefully you can see that S from R to S then, right? No, sorry, O to S is three lots of OR. So if O to R is one part, then O to S, well actually it's firstly going to go from O to R, which is already one part, then it'll be two more parts to get from R to S, right? So overall, O to S is going to be three lots of O to R. Hopefully you can see that, right? But I've labelled the parts, right, the relative parts or the ratio of each vector or each side. I've labelled that on my diagram. That's what the numbers mean. Okay, right. And we also, and that's what we're given. OP is A and OQ is B. I've labelled the vectors A and B on my diagram. Right, that hopefully you understood how I label the diagram in that way, in particular with these numbers here, so the ratios here. So RQ is 2 lots of PR. So again, to recap, P to R is there, that's going to be one part. So then R to Q, that vector there, is going to be 2 lots of that, so hence double P to R. So 1 to 2, right? And likewise, I have OS, so the vector from O to S, which is this massive line here, that's going to be 3 lots of O to R. So O to R is one part then O to S, right, is going to be 3 parts. So O to R, right, and then R to S. So that's going to be another 2 more parts to get 3 overall, okay? Right, okay. We then need to show that firstly, OS is 2A and B. So we need to find a vector for OS, right? So, O to S then. Well, I know this. I know that OS is 3 lots of OR, right? I can start with that. So then I need to find a vector for OR, right? So OR then, so that's going to be the vector here, right? From O to R. But obviously I don't know a vector for O to R directly, so I need to find another way of getting from O to R. So it's all about finding different paths, right, to get to the same vector. So I need a different path from O to R. Well, I recognise I can go from O to P, right, along A. So O to P, then P to R, right? And there we are. I then start at O and end at start at O, end at R. Okay, there we are. So and again, that's going to be 3 lots of that. Sorry, so it's going to be 3 lots of, right, the vector OR, which we can go from O to P, and then P to R. Right, and then well, we know O to P is the vector A, so I can fill that in. But then P to R, well, I don't know anything about P to R, but I do know P to R is one part of the line on P to Q, right? P to Q, we can see is 3 parts in total. R to P, P to R is one part, and R to Q is 2 parts. So that means P to R, we can say is a third of P to Q. And that's utilising the fact that P, R, and Q, if I draw that line out, they're all on the same straight line, and in particular R to P is one part and R to Q is 2 parts, right? So overall it's going to be 3 parts on P to Q, and what that means is that the parallel, so PR is going to be a multiple of PQ, right? And it's a third because of the way that they told us to split the ratio. Okay, hopefully you can see that PR is a third of PQ, the whole line P to Q. Okay, so how then we need to find P to Q because we're not given P to Q either. Okay, so now we need to find another vector for vector for vector. So now we need 3 lots of A, and then we need a third of PQ. Now PQ, we need to find an expression for P to Q. So that line there. Well, actually, if we want to go from P to Q, right, we can go from P to R, P to O, then O to Q. I have both of those vectors, right? So that'd be PO, but obviously PO, I know O to P is A, but I want to go the other way. I want to go from P to O instead. So it's going to be the negative of OP, and then O to Q. Okay, and then I can work this out. So it's going to be 3 lots of A and a third, and then minus OP. Well, as we discussed, O to P that way is A, but I want to go the other way from P to O, so it's going to be negative of that. So it's negative of A, and then O to Q, O to Q, O to Q that way is just B. Okay, the vector B, and there we are. Well, actually now I've just got I've got definite numbers, right? I've got A and B only. So there's no unknowns, so I can now expand this and simplify. So it's going to be 3 lots of A. Then if I expand this inner bracket, so it's going to be a third minus a third of A, add a third of B, And so then if I simplify the inner bracket, I get 3 lots of A minus a third A is going to be 2/3 of A, add a third of B. And then if I expand this one last time, I get 3 times 2/3 of A, which is 2A, and 3 times a third B is B. Well, actually, there we are. We've shown that OS is 2A at B. Well, there we are. Cool. There we are. Nice. Then for part B, we then need to show... Oh, we're given a point T now, which is added onto the diagram such that O to T is minus B. Right, so we can add that on, okay? So O to T then, we're told O to T is negative B. Well, we know O to Q is positive B, so the vector B is that way, right? So to go to the other way, to negative B, it's going to be in reverse, right? It's going to be the opposite direction from O to Q. It's going to be that way instead. Which means if we start at O then, O to T, that way, if we continue the line on, it's going to be the vector that way to T, right? And that'll be negative B, okay? So there we are, okay. So you just need to remember that minus B is going to be the reverse direction of positive B, so that vector there. Okay, so that's O to T. We added that on. We then need to show that the points T, P, and S all lie on the straight line, okay? So the aim of this then, if T, P, and S lie on the same line, then we need to show that we could, if we make two vectors out of this, so say, let's do TP and TS, right? Or PS actually, let's say. Then we can show that, for example, T to P and PS are multiples, right? Or the parallel. Which means that we can say T to P is K lots of PS, right? So if we want to show that 3 points are on the same line, if we make two vectors from any 2 points in the line, so say from T to P and then P to S, those two vectors, right, are going to be parallel, so they're multiples. That's what we want to show. If we can show that, then they're on the same line, okay? It just goes back to what I talked about earlier at the start. But that's the aim. So then we're going to consider then the vector TP, first of all. Okay. Oh, I could also find the other possible vector I could perhaps find, not instead of TP and PS, I could find T to S as well. Okay, that's another possibility. But I'm going to stick with these two and see where I go. Anyway, so T to P then, if we look at our diagram up here, right, that I've drawn, T to P, if we're going to start at T and then end up at P, well, I know O to T is negative B, so if I want to go the other way, it's going to be positive B. So T to O then, first of all, and then if from T to O to get to P, I need to go from O to P, right? There we are. Well, T to O, as we discussed, is positive B, and O to P then, once we've got from O to P is going to be A, the vector A, as we can see on my diagram there. A. And that's it. So there we are. That's my vector TP. But we also need to find another vector, right, between TP and S. So I said, now let's find, say, PS, right? So PS then, if we then find that vector, so we're going to start at P and end at S, right? Well, to get from P to S, I can go from, well, I could go from P to R and then R to S, but I think it might be a bit simpler to go from P to O and then O to S, because I know what O to S is. I found that in part A, right? So again, it's a very good idea to use vectors you already know. So I'm going to use the fact I know what OS is. So to go from P to S, I can go from P to O and then O to S, okay? And again, P to O then, firstly, from P to O, right there, right, it's going to be the reverse of vector A. So A, right, is that way. You can see in my diagram, right? But so then to go the other way is going to be negative of A, right? Then from O to S, well, we know what OS is. We worked that out in part A. O to S was 2A, add B. So then if we collect the like terms, so then 2A minus A, that's A, add B. Well, what do you know? They're both equal, actually. They're both equal. So therefore TP is equal to PS. Right? So then that means then they're multiples of each other. Well, actually, they're a multiple of 1, technically. It's 1 lots of PS, but it's still a multiple. So it's still a multiple PS. So therefore, we T to P is a multiple of PS. And I'm also going to say P, right? P is a common point in both vectors, right? You have to put that extra point in. And P is a common point in both vectors. That's crucial as well. So therefore, TPS is a straight line. And there we are. So that is a very common proof. That's the main sort of common way of proving that 3 points on a straight line. You need to show that. So to recap, we found that 2 vectors on the line, say T to P, then P to S. They're both multiples of each other. Well, in this case, they were equal. So that'd be a multiple of 1, but still a multiple. So they're both multiples. And also then, because they have a common point, which is in this case P, there will always be a common point if you find 2 vectors from the line. Then that means it has to be a straight line. The main reason, by the way, why you have to mention that there's a common point in both vectors in this way. Say if we found T to P, right? But then what if there was a different, what if P was somewhere else? What if P was in here and then we got from P to S, right? T, P, PS. They're not on the same straight line. They're both parallel, right? They're both the same line, but they're not on the same line because they're different, right? They're separated. So because if there's a common point, then that forces the next vector to be continuing on, right? So then that'd be P to S. So you have to mention that there's a common point on both vectors when you're proving that there's 3 points on the same straight line. Okay. And also we could also rephrase this last bit. You might see this terminology. You could also say that points TPS are what we call collinear. Now, collinear just means on the same straight line. Okay, it's another way of phrasing is on the same line. Okay. Right. Okay. Now we're going to look at an exam question on this. Right. So we are given a triangle OAB. The point C is such that O to C is 2 lots of OA. So we're probably going to, we're going to need to extend our diagram again. So O to A then, O and then say A up here. And then we have A to B. And then obviously B to O again. So we've got the triangle. We're told firstly that the point C is such that O to C is 2 lots of OA. So if OA, right there, that's O to A, then O to C is going to be another lot of that, right? So if OA is 1 part, then if we extend A to C here, then that's going to be an extra part, because then overall from O to C, that's going to be 2 parts, right? So it's going to be double lots of O to A, okay? So there we are. We're also given, so we can add that on. We're also given point M is a midpoint of A to B. So M is going to be in the middle of AB there, such that this is going to be one part, and then M to B is going to be one part as well. Okay. So there we are. So midpoint means you split either side of it equally. So each of these is one part each. Okay. So the whole line A to B is two of those parts. Now, we were also told that the straight line through C and M cuts O to B at the point N. So straight line through C and M. Let's just draw that right from C to M. Then if we continue that line, we reach a point on the it cuts OB. We're told it cuts OB at the point N, so we can label that N there, right? Right, okay, we're also given that OA is vector A, so that's going to be, let's do A there, so that'd be one part. So that's vector A from O to A, and vector B is OB there, okay? Right, so a lot of information there, actually, a lot of information. Again, hopefully you are comfortable with how I did this sketch, right? So I had to... how I added the point C on, right, and why the M is the midpoint. It cuts the line AB in two equal parts, and then yeah, so that's my diagram of all the information given. Right, we first then need to find C to M, the vector CM, right, in terms of vectors A and B. So we need to find an expression from C to M. Now, obviously that's going to be the vector there from C to M. Obviously I don't know that directly, but so I'll need to find another way. Now, I know that C to M then, I can go from C to A and then A to M, right? I can go from C to A, then A to M. Now, at C to A then, well, that's going to be the negative of A. I've drawn this vector here from A to C, right? So it's going to be the negative of that, right? Whatever that is, it's going to be the reverse of AC. AC is that way, but I want to go the other way from C to A instead. So it's going to be negative AC. And then for A to M, right? A to M. Well, A to M, again, is the mid here. M is the midpoint of AB. So I can say that A to M is a half of AB, right? Okay. Right. Well, A to C then. Okay. Well, A to C then. I don't know what AC is either directly. I'm not given that information directly. But what I do know is that A to C then is one part of the line from O to C. Right? So it's going to be a half of OC, right? So minus the half of OC, add a half of AB. Now, to then find AB then again, well, AB, let's refer to this triangle here, right? A to B, that way, I'm not given that vector either, but I can find another path, right? I can go from A to O, and then from O to B. Well, A to O then, I know that O to A is vector A, so from A to O, instead it's going to be the negative of that, right? So it's going to be negative vector A, and then then from O to B, right, it's going to be the vector B, right? Because I'm given OB is B. Okay. Okay. So then I have, well, okay, mine is a half of OC, but I need to find what OC is, right? I need to get that as an actual vector. So I need to keep I need to keep decomposing vectors, right, until I get an actual vector. So then O to C. So I then need to find O to C. Well, as we discussed, O to C, right, tells me here, OC is two lots of OA. But what's OA? OA is just the vector A, so it's going to be 2 lots of A then, right? There we are. And then I can just expand this, right? So it's going to be minus a half of A, add a half of B. But then there we are, we've finally got there, okay? So then it's going to be minus half times 2A, it's going to be minus A, minus a half A, add a half B. That is going to be minus 3 halves of A, add a half B. And there we go, that's the vector C to M. Right, okay. Now we need to now we need to show that ON, now the vector O to N, which is going to be here, right? That's going to be, we need to show this vector can be written in this way. So we need to find an expression for the vector ON, essentially. And then hopefully we get to this expression, right? ON then. And now we need to consider ON. Well, again, ON, I don't know ON directly. So I need to find another way I'm getting from O to N, right? Now, and by the way, this might be a bit misleading. It isn't the vector B, right? The vector B is for O to B, right? O to N is not B, right? I don't know exactly what ON is. Sorry, I should probably clarify. A bit misleading. That's going to be B for the vector O to B, not O to N. Anyway, so to find O to N, then I can't do that directly. So I need to find another way I'm getting from O to N. Well, actually, I've already worked out what C to M is in part A. They didn't ask me that for no reason, right? And I'm going to need to use that vector, probably, right? It might help. So I can use that when I consider my path, right? If I want to go from O to N, then I could also go from O to C, and then C to N, right? So it's going to be O to C, add C to N. Well, OC, as we just discussed, OC is 2 lots of OA, and OA is A, right? So it's going to be 2 lots of A. OC is 2 lots of vector A. And then C to N, right? Well, C to N, right? C to N, I don't know the vector for, so I could try and find a way of getting from C to N by finding a path, but you might be a bit stuck there. What we can use instead is, again, the fact that CMN is a straight line, right? We're pretty much told that in the question, right? The straight line through C and M cuts at the point N. So C, M and N are on the same line, which means we can make vectors out of them because they're going to be parallel. So so that means then if I can make vectors out between any two of these 3 points, so then I can say that the vector C to N, well, actually C to N, right, is going to be parallel or multiple of C to M, right? So it's going to be K lots of CM, right? And so there we are. So hopefully you're happy with that. If I were to sketch that again, right, if I were to just draw that line, right, from C, M and N, hopefully you can see it here. C, M and then N. Again, they're all on the same straight line, but also then you can see that the vector from C to N, right, the whole line, it's the same it's the same direction, it's the same sort of gradient from C to N, right? So they're parallel. So the vectors from C to M and C to N, they're all parallel, so they're multiples. That's how I deduce this, okay? Right, so I can substitute that in then. So C to N is going to be K lots of C to M. But I know what Cn is, so I'm using the fact that, which is here, right? This is from part A. C to M is this. That's what I've worked out before. So it's going to be 2 lots of A, add K lots of this, right? Minus 3 halves of A, add a half of B. So then if I expand it, it's going to be 2 lots of A, minus 3 half lots of A, 3 halves K lots of A, sorry, add a half K lots of B. So then lastly, I can probably sort of factorise, right, the A part, right? So it's going to be 2 minus 3 half lots of K lots of A. add a half k lots of b. Let's compare with my answer then. So I have 2 minus 3 half lots of this sort of weird symbol, right? I'll talk about that in a second. This symbol, right? This letter, right? Lots of a, add a half of this letter, lots of b. But that's actually the same as my answer, right? My answer is in this exact form, but instead of this letter here, I have k instead. That's fine. The fact is, it's just a letter at the end of the day. The question decided to use this letter instead, but they're both just letters, right? I can then replace this by saying 2 minus 3 half of this letter. Now this letter is called lambda. Hopefully I spelled that right. Actually, I think it might just be lambda. Okay, it's a Greek word for this symbol. It's often used with vectors, which is probably why the question used it. But you can use any letter you want. Any letter. It could be A, it could be K, it could be T, it could be R, it could be absolutely anything. They decided to use this symbol lambda, but it's just a letter. It's just a letter. But I can replace that then by just saying K equals lambda. It doesn't matter, right? It doesn't matter. They're both just placeholders for a number, right? So it's going to be minus 3 halves. Then instead of K, I'm now going to say lambda. Lots of A. Add a half lambda B. And then I get what they wanted, right? That's what the question wanted. There we are. That's part B done. Then for part C, then they want us to prove that O to N and then N to B is 2 to 1. Lastly, right? So obviously this ON, right, is on the line O to B. They want to basically want us to show that from O to N it's 2 parts, then N to B is 1 part. That's what they want us to show, right? Okay, well, we have this expression for ON already, but the problem is with this ON, I have an unknown. I have this lambda, which is a constant, right? This lambda is a constant. So I can't work out the vector ON directly, which means I need another way of getting from O to N, right? I need another different way of getting O to N. Well, again, I could maybe try and find a different path. But again, you're probably going to get a bit stuck for finding a different path, right? Because the problem is, if you try and find a different path for ON, that doesn't use O to C, then C to N, like we did last time, you're gonna be implicitly using the same information, so you're gonna basically end up with the same equation, right? So you probably won't be able to find a different path that'll tell you something actually new, right? But the other thing we can consider, again, the key thing with these questions is to utilize the fact that things are on straight lines, right? O, N, and B are on the same straight line as well, right? O to N to B is a straight line as well. So again, we can do the same idea of creating vectors out of this. So I can say that the vector O to N then, well, again, is going to be a multiple of the vector O to B. If I create, from any 2 points on this line, O to N and O to B, these 2 vectors have to be parallel, or the multiples. So it's going to be then K lots of OB, right? I can say that, right? Again, if you look at my diagram here, O, N, and B are on the same straight line. So the vector from O to B, right, it's the same line, so the same direction as O to N, right? So they're parallel, so the multiples, okay? So I can say this here, okay? So then I can substitute it in. So I can also say that O to N is K lots of OB. But I know what OB is. OB is just the vector B, right? It's just vector B. Oh no, sorry. I need to substitute that in. So it's going to be K lots of B. Well then, hang on. We got 2 different expressions for O to N. Right? So I've got expression 1 here and expression 2. But because it's the same vector on, that these two expressions have to be equal, right? So if the first one equals the second one because it's the same vector, then we can say that 2 minus 3 half lambda lots of A add a half lambda B is going to be K lots of B, right? So hopefully you can see that. I equated the first expression with the second one because it's the same vector on, right? On. They have to be the same. But then I can compare coefficients then. So I can compare the A part and the B part, right? Well, actually, if you look at the first part, 2 minus 3 half lambda lots of A, there's no A on the second part. Well, actually, that means that it's 0 lots of A, right? Effectively, if there's no A, then it's 0 lots of A. So then I can just say that's 0A, or then that we can say then that 2 minus 3 half lambda is 0. So then I can solve for lambda, right? So then I can say that 3 half lambda equals 2. And so therefore, lambda, if I divide both sides by 3 over 2, I get lambda is 2 divided by 3 halves, which is 4/3. So there's my lambda then. I can also then find K, right, if I wanted to. I could then say, if I then compare the B coefficient, right, I could then say a half lambda B is KB, right? So the B parts are also the same. So then I can say that half of lambda equals K, but I know what lambda is. K then is going to be half lots of lambda, which is 4/3. And so K then is going to be 2/3. And there we are. Okay, so now I know what K is. I know what lambda is as well. But actually then, if I go back to my expression, then ON is K lots of OB, right? So ON is K lots of OB. But I know what K is. ON is 2/3 of OB. And there we are. So then that means then, that what that actually means, right, in terms of a ratio or whatever, ON is 2/3 of the way of OB. So it's 2/3 of the way of OB. If I add that onto my diagram then, that means O to N is 2/3, right? O to N is 2/3, which means N to B, the remaining part of OB, has to be a third then. But then as a ratio, you can then see that ON to NB has to be 2:1, right? 2/3 here and a third there. So I'd say then that what that means is, and NB is a third OB. So therefore ON to NB is going to be, well, you could say 2/3 to 1/3, right? If you really wanted to be really clear, but then you could just cancel. You know, with ratios, you can cancel down by the same amount. You can simplify it like a fraction. So to cancel the third out, you can get 2:1. And there we are. There we are. Very, very tricky question. That is. These are all very tricky questions. But yeah. So there we are. If I do remember correctly, a lot of students didn't pick up most marks, if not all, at any really. But this question is probably one of the worst scored questions. So it's very, very hard. Right? Very hard question. But hopefully that made some sort of sense. Hopefully, you sort of can sort of pick up the sort of way to approach a question like this now, with this sort of finding different paths, or using the fact things on straight lines to create vectors that are multiples, and yeah. Okay, but that is this first segment done, to do with comparing coefficients and using vectors in this sort of way, geometrically. So all to do with finding different paths, right, along different sides of a shape. But that's the first bit of this section done. Okay, now we're going to look at the second type of question to do with geometric problems with vectors, and this one's probably the easier one. Okay, and it's to do with trigonometry, and really, and what we can do is we can consider if we're given the sides of a shape like this with a triangle, we're given the sides as vectors, right? So we know that AB is 3i minus 2j here, and A to C is I minus 5j. We need to find the angle BAC. So A is in the middle, so it's the angle at A. I'll call that theta. Now we need to find that angle, right? But I only have the sides of vectors. So how you can tackle these questions is to find the magnitude of the vectors, because that will then give you the length of the sides. Then once you found the length, it just becomes a standard trigonometry problem. So, okay, if I then get rid of all this then outside, I firstly then need to find, with these sort of questions, you should consider finding the lengths of all the sides. So firstly, A to B here, A to B is 3i minus 2j. So therefore the magnitude or the length of A to B is going to be obviously the root of the x and of the I and the j parts squared. So 3 squared add minus 2 squared. That would be root 13. Okay, so I can add that onto my diagram then. That's root 13. I can then do the same for A to C. So therefore the magnitude of AC is going to be the root, well, I is again just 1i, right, effectively. So it's going to be 1 squared add minus 5 squared, which would be root 26. There we are. Well, hang on there. We need to find the last side here, B to C. I'm not given BC, but I can find it out by using the vectors. If I then consider the triangle again from B to C, or C to B, doesn't really matter, but from B to C, right, that vector there, I can then go along, I can go around the triangle. From B to C then, I can go from B to A, then A to C, right? And then therefore, I can find BC. So B to A, add A to C. Okay. But B to A then, I know AB is this vector. I know what AB is that way from A to B, but I want B to A, so it's going to be the reverse. It's going to be negative AB, add AC. Now AC then is I minus 5j. Okay, so then minus AB is going to be minus the vector AB, which is 3i minus 2j. Minus plus I minus 5j. Then I just need to expand it and simplify, right? Well, I can collect the terms. So minus 3i add I is going to be minus 2i. Then minus 2j is a double negative, so it'd be plus 2j minus 5j, that'd be minus 3j. And there we are, that is my vector B to C. Okay. So then the magnitude of that, so the side BC, the length of that is going to be the root of minus 2 squared plus minus 3 all squared, which will get me root 13. And there we are, we can fill that in. BC is root 13. So now we know we have all three sides. So if I was to then draw that triangle out then to really show case what's going on. A to B we know is root 13. We know B to C there. We know B to C is root 13, and we know that A to C, what was it, root 26. And so then it asks to find the angle BAC, so the angle at A, right there, which was theta. So if I highlight that on, there we are. So hopefully now you can see with this triangle, once we just found the length of all three sides using the magnitude of the vectors, it's now just basically a standard trigonometry problem. So how can I find theta then if I got all three sides? If I have three sides and an angle, that's the cosine rule, right? So now that's just standard trigonometry. We looked at that in chapter 9, the cosine rule, even from GCSE as well. But then we can say that, well, the angle theta then is opposite the side of root 13. So it's going to be root 13 all squared. So it's going to be a squared is b squared is c squared minus 2 lots of b times c cosine of the angle. So that means root 13 squared is going to be the upper two sides all squared minus 2 lots of root 13 root 26 cosine of theta, right? And we want to solve for theta. So now we can just sort of simplify this. Well, root 13 all squared, well, the root sort of cancels, right? If I'm square rooting, but then I'm squaring, that just goes to 13. And then that's going to be 13 add 26. Minus 2 times root 13 times root 26. If I do that, I get 13 root 2. Hang on. Now we get minus 26 root 2 cosine theta. Okay, cool. So then I can then simplify this. So if I do 13 take away 13 take away 26, I get minus 26 is equal to minus 26 root 2 cosine of theta. So therefore then if I divide by 26 root 2, I get cosine of theta. It's minus 26 over minus 26 root 2. That would be 1 over root 2. And then therefore, if I do inverse cos, I get theta to be 45 degrees. And there we are. Okay, so that's the angle then. Cool. So again, as you can see, once you just find the sides by using the magnitude of the vectors, it just becomes a standard trigonometry problem. Okay. Right. Okay, so the final part of this chapter, of this video, sorry, is going to looking at different types of shapes, and in particular, we can use vectors again with like the sides of the shapes to prove certain properties or prove some, as for example, a triangle might be an equilateral or an isosceles or a scalene triangle. And these are the shapes and their properties that you do need to be familiar with. It is from GCSE, but again, A level will assume some GCSE knowledge that that's not explicitly covered. So I thought I'd cover it here. Okay, so these are the sort of shapes you will be expected to know, and the properties, and how we can use the properties to then prove for example, a quadrilateral is a square, right? So let me go over it then. So firstly, the triangles. That is, this is probably a bit easier, right? So firstly, an equilateral, all sides are equal. So going to, again, be focusing mainly on the sides. So it's quite similar to the last sort of mini section where we looked at the sides or the magnitude of the lengths to then, then we can use the sine rule or whatever. In this case, we're going to then find the length. They're going to find the length of all of the sides of the shape to consider what type of shape it is, okay? And these criteria will help us here. So again, firstly, an equilateral triangle is 3 equal sides, so they're all the same. An isosceles is where 2 sides are the same, but not 3. A scalene then is where no sides are equal. There's also another type of triangle, and that is obviously a right-angled triangle, like this, where obviously it has a right angle, okay? But more has a right angle. But more specifically, in terms of the sides of a right angle triangle, if you're given the sides and you want to show it's a right angle, you need to show that Pythagoras theorem applies. So if we have the length A and B and C, So then you need to if you give them the sides, then you need to check that a squared and b squared is indeed equal to c squared, the hypotenuse. Okay. So if you want to if you have the sides of a right angle triangle, and you want to show it is a right angle triangle, if you have the sides, the length, then you need to again just verify that Pythagoras theorem applies by squaring all the sides. So that's the triangles. That's fairly simple. Now quadrilaterals then as well. So that these are four-sided shapes. So firstly, a rectangle. We have again two opposite sides. The two pairs of sides are the same. So the width is the same and the length is the same size. But in addition, the angles are right angles. So if you have an instance where so then two pair of sides are the same, you then need to check that there's a right angle between them. Okay. A square then is kind of like, it's a type of rectangle, but instead of just two pair of sides being the same, all the sides are the same. Okay. And it's right angled as well. Okay. Then we have a parallelogram, and a parallelogram is like a rectangle in the sense that two pairs, the opposite sides are equal, right? Opposite sides are equal, like a rectangle. But the angle doesn't have to be a right angle. So all you then need to show is that the parallel. Okay, so the opposite sides are parallel. Okay. But actually, instead, you can show that the opposite sides are equal. Okay. Then we have something called a rhombus, which doesn't really come up really even at GCSE. So I imagine a good few people be like, I don't remember this. That's fair enough. We cover it here. A rhombus then is actually a parallelogram, but all the sides are equal. Okay. So actually, again, a rhombus is a type of square. A square also has all sides the same, but a rhombus doesn't have to be right angled. Okay. You just need to all you need to show is that all the sides are equal. Exactly the same for parallelogram. The parallelogram is like a rectangle, but a parallelogram you just need to show that the opposite sides are equal. You don't need you then don't need to show it's right angled. With a rectangle, you then do need to also show the angles are right angles as well. But that's a rhombus then. A trapezoid, or what we call a trapezium, another name for it, is when two sides are parallel. Or just two sides are parallel. Okay, now that's slightly different to a parallelogram, where both opposite sides are parallel, right? In the trapezium, only one of them are parallel, which is the top and the bottom side there. So that's the difference between a trapezium and a parallelogram. And then lastly, a kite. Okay, again, a very uncommon one as well, but do pay attention. And that's where two pairs of adjacent sides, so the sides next to each other, so that side, and also this side and this side. Okay, so both pairs of adjacent sides are the same length, so it's different to say a parallelogram, because obviously again opposite sides are equal, but they're opposite. In a kite, the key property is that they're adjacent, they're not opposite. Okay, so the sides next to each other are equal. In a parallelogram, the opposite sides are equal, not the sides next to each other. Okay, so do sort of familiarize yourself with these properties, and again you can consider the lengths of the shapes to consider what type of shape it is. Okay, so we're going to work with some examples then with this in mind. And we got this example first. We're given in the triangle ABC. Again, I'm going to do a rough sketch of a triangle. A, say B here, and then C. Okay. ABC, AB, the vector AB is 9i and 2j, and A to C is 7i minus 6j. We need to find B to C, right? We need to find B to C first of all. Well, again, we can use our sketch to say that B to C, if we want to go from B to C, we can also go from B to A and then A to C. Well, B to A again is the reverse of A to B. So we can do negative AB. And then A to C. And there we are. Well then, if we just then substitute these vectors in, AB, so negative 9i add 2j, and then add AC on, that'd be add 7i minus 6j. And then lastly, if we just combine the I and j parts, well, minus 9i add 7i is minus 2i. And minus 2j minus 6j is minus 8j. And there we are, that's my vector BC. Cool. Then for part B, and this is where it kicks in, we need to prove that this triangle is isosceles. So again, we're going to consider all the length of three sides. So firstly, we can find the length AB. Now we know AB is 9i and 2j, so the length of that is going to be the root of 9 squared and 2 squared, which will get me root 85. And then the other side be AC, right? The length of AC. Well, AC is 7i minus 6j, so it's going to be root 7 squared add minus 6 squared, which would get me root 85. Well, that's great, because now we know that two sides are equal. But then we also need to check BC, the other side. So the length of BC, well, we found BC in part A. So it's going to be root minus 2 squared add minus 8 squared, which would get me two root 17. So that's different. But what we can see then is that exactly two sides are equal. So what that means is, if we go back to our defining property list, right, defining properties, if we go back to our list here, an isosceles triangle has two equal sides. We found that there were two equal sides, so it has to be isosceles. And there we are. So that is the whole idea of proving if something is isosceles, or something's a trapezium, or something is a rhombus. We will look at more examples, but that's the whole theme, right? There. Okay, part C. We then need to show that cos of the angle ABC, so the angle ABC, so angle at B, because B is the middle, right? The angle theta then, is this, 1 over root 5. Now, we know the lengths then. If I add on the length that I know, well, AB is root 85, AC is root 85, and BC was 2 root 17. Yes. So then I can use the cosine rule to find the angle theta, right? So then I can say that, well, if I use cosine rule, well, the angle theta, right, at B is opposite the side root 85. So then I can say root 85 all squared via the cosine rule. It's going to be the other two sides all squared. So root 85 squared at 2 root 17 all squared minus root 85 2 root 17 cosine theta. So then I just need to simplify all this, put it in the calculator. Well, root 85 all squared, well, the root cancels, just get 85. Then that's going to equal 85, add, well, 2 root 17 all squared. That's going to get me 68. And then minus root 8, that'd be minus 2 lots of this, okay? So minus 2 lots of root 85 times 2 root 17 gets me minus 68 root 5 cosine theta. So then I can then sort of simplify a bit more. Well, 85, if I then subtract 85 to both sides and then subtract 68, I get minus 68 is minus 68 root 5 cosine theta, right? So then I can then divide by minus 68 root 5 to get cosine theta is minus 68 divided by minus 68 root 5. And so therefore cosine theta is 1 over root 5. And there we are. There we are. Great. Cool. Okay, now we've got some exam questions on this. So we are told, relative to a fixed origin O, the point A has position vector this, the point B has this position vector, and C has that position vector. We firstly need to find AB. So again, I'm going to consider a sort of triangle between these points. So ABC. Well, actually, no, we don't need to do that, actually. Think about it. AB, if you're given the position vector of everything, the position vector from O to whatever, well, A to B then, we can express that as the position vector of the second point, so B, minus the position vector of A, right? And so there we are. We looked at that last time with position vectors. We can express any vector in this way. So then we can say O to B, well, that's going to be 3i minus 3j. Subtract OA, so that's position vector of A, that's going to be minus 2i and 5j. If I do that then, well, 3i minus 2i is going to be I, and minus 3j minus 5j would be minus 8j. And there we are. So that's my vector AB. Cool. Then it says, show that the quadrilateral OABC is a trapezium. Okay. Right. So, if I imagine then, I have some sort of trapezium, right? Say O, then A, then B, then C, right? Imagine it looks a bit like this. Just a rough sketch of a trapezium, right? I can kind of imagine that the top side, AB, is going to be parallel to OC, right? I can sort of imagine that, right? Well, I know what AB is. What's OC? Well, OC is given to me. It's 2i minus 16j. Well, hang on then. I need to know they're parallel. So what I'm saying is that the top and the bottom side have to be parallel, right? Well, that means AB is parallel to OC. And we can see that, right? We can see that I minus 8j is going to be half of this. It's going to be half of 2i minus 16j. So therefore, they're multiples, right? So AB is a half of OC. So therefore, because one vector is multiple of another, that means AB is parallel to OC. So what that means is then we have one side or one opposite side that's parallel. So we have therefore one. So therefore there is a pair of parallel sides. So therefore it has to be a trapezium. So therefore OABC must be a trapezium. And again, that stems from my defining properties. If I go up here, if we want to prove something is a trapezium, prove something is a trapezium. If you look at here, two sides are parallel. That's what it did. We've shown that two sides, so the two vectors were parallel. And so there we are. Therefore, it has to be a trapezium. Simple as that, right? Simple as that. Cool. So yeah, so again, AB and OC are two sides, and we've shown that AB is parallel to OC, so we've got two sides that are parallel to each other. Great. Okay, one last question then. We are given a parallelogram PQRS. We're given that PQ is 2i plus 5j, and we're also given that QR is 5i minus 2j. We need to show that this parallelogram is a rhombus. So a rhombus, remember, that all sides are the same length, which means we're going to need, if PQ is that side and QR is that side, then we need to consider the lengths, right? So that, let's get cracking. We get the magnitude of PQ, the length of PQ, which is this. It's going to be the length of 2 squared and 5 squared, which will get me root 29. And also QR then, well, the length of QR, again, it's going to be the root of 5 squared add minus 2 all squared, which again gets me root 29. Well, there we are, they're equal. So that means the length of PQ is equal to the length of QR. So then, well, actually, you're probably thinking to yourself, well, how come then that shows all the sides are equal? I'm just showing 2 sides. Well, we're already told it's a parallelogram. A parallelogram, well, again, the opposite sides are parallel, but they're also equal. Okay, so that means PQ, the length of P. If we know the length of PQ, then, which is now root 29, oh, that means then that SR is also root 29. Okay, because opposite sides in a parallelogram are parallel, but they're also equal, right? If we go back to our properties, a parallelogram, 2 pairs of parallel sides, so the sides are parallel, the opposite sides are parallel, but they're also equal. The opposite sides are equal. That's a key property of the parallelogram. So there we are, okay? And likewise then QR is root 29. So then that means that PS is also root 29, but therefore all 4 sides are the same, okay? And so therefore I would also say that the lengths, the other 2 lengths then, the length PS and SR is root 29. As it's a parallelogram. Well, then that's it then. We're showing that all 4 sides, so all sides are equal in length, or have equal length, right? So therefore it has to be a rhombus. So therefore, what was it? PQRS is a rhombus. And there we are. So again, once you do just pick up once you pick up the defining properties from this list, of properties of these shapes. So again, a rhombus, well, that's a parallelogram with all 4 equal sides. So it has to have all sides equal. So once we then once we find all the lengths, then there we are. So then they're all equal. So there we are. So once you learn that, it's actually quite straightforward to kind of prove a shape is a rhombus, or a shape is a trapezium, or an isosceles, or whatever, right? Okay, then part B then, once we've done that, we need to then find the area of this rhombus, right? Okay. Well, I have all the lengths then, what can I do here? What can I do? Well, if you remember when we looked at in the triangle chapter, I think it was chapter 9 again, I'm going to redraw this, right? So again, that's PQRS, and they're all root 29. All sides are root 29, right? Well, if we know that, what we looked at in the triangle chapter is we could actually consider the diagonal, and then it splits it into 2 equal triangles, right? Which means if we can find the length of both triangles, the area, sorry, of both triangles, then we get the area of the whole shape, right? But then the question begs then, well, how do we find the area of a triangle, right? So area of triangle, So area of triangle, let's say the area of this triangle here, right? PQS. Right? Well, we know that's root 29, and we know that PQ is root 29. Right. Well, we're probably going to have to resort to using some sort of... Well, we know the area is going to be half AB sine C, right? Of the triangle. It's not a right angle triangle. Not necessarily. Not necessarily. Don't know anything about the angles. So we're going to need to use half AB sine C for this triangle. But we know these two sides already, don't we? Right, so then we just need to find the angle here. I'll call that theta then, right? Theta. And then we can find the area of the triangle, right? And then once we find the area of that triangle, then we can double it to then get the whole thing, right? Because again, the two triangles are equal. So we find one area, we can double it to get the other one. There we are. So we just need to find this angle theta then, okay? Now, well, in order to do that, to find the angle theta, I need to either find another angle or I need to find the diagonal QS. But actually, I can work out QS because I'm given the vectors. The vector QS then, if I then consider, I'll do it down here, right? Angle QS, right? If we look at this, if we look at our vector, right? If we look here, right? If I add the diagonal on to Q to S, there. Well, actually, then, if we let's say we from Q to S, then we can go from Q to P, and then we can go from P to S, right? So therefore, Q to S is going to be Q to P, and then P to S. Okay, but Q to P then, I'm given P to Q, right? But I want Q to P, so it's going to be the negative of that. So it's going to be negative PQ, add PS. But actually, PS then, if we go back to my diagram, let me get rid of these lengths. Okay, probably a bit unclear. I want the vector QS, right? So I'm going from Q to P, which is there, and I want to go from P to S. But actually, P to S then is going to be the same vector as QR because it's a parallelogram. The opposite side is equal. I know what QR is. It's 5i minus 2j. So that PS is going to be 5i minus 2j. So then the negative of PQ then, so PQ is 2i at 5j. So negative lots of that. Plus 5i minus 2j. Well, then if we add the I and j's, well, minus 2i add 5i will be plus 3i. And then minus 5j minus 2j will be minus 7j. So that's the QS. But so then the length of QS is going to be the root of 3 squared add minus 7 squared, which will get me root 58. So now I also know the length of the diagonal. It's root 58. So I can add that onto my diagram here. But now I'm in the instance where I know all 3 lengths of my triangle, right? So now I can use the cosine rule to find theta, right? I'll do it up here. Right, I've got a lot of room. Cosine rule. So then I'm using the cosine rule to find again theta in this triangle. Well, theta is opposite the length of root 58. So then I can say root 58 all squared. It's going to equal the other two sides all squared. So root 29 squared add root 29 squared minus 2 lots of root 29 times root 29 cosine theta. Okay. So then I just need to work all this out. Well, root 58 all squared, well, the root squared, well, that just leaves us with 58, right? And then that's going to be 29 add 29. minus 2 root 29 root 29. You can put that in the calculator, or you could realise the two roots will effectively square each other out. So minus 2 lots of root 29 root 29 will get me minus 58 cosine theta. And then I can just simplify, right, this equation now for theta, cos theta. Well, 58, if I subtract 29 and subtract another 29, well, 58 minus 29 minus 29 gets me 0. So therefore I have minus 58 cosine theta equals 0. So therefore cosine theta is 0. So therefore theta is going to be 90. Well, oh, there we are. So it is a right angle. Okay. So this tells me that this theta is 90. So actually we're dealing with a right angle triangle. So, well, in this case, we can still do half AB sine C. So it's going to be half of, in this triangle here, half of root 29 sine 90. And then if we put that in the calculator, well, sine 90 goes to 1. So it's sort of half times root 29. So it's 29 over 2 units squared. Okay? And that is my answer. Okay. Cool. There we are. Oh, no. Sorry, my apologies. No. That's the area of the triangle, of this triangle here. The area of the parallel of the whole rhombus is twice that. Then we need to account for the other triangle. So therefore, area of the rhombus is double this, right? Because it's two lots of the triangles. So it's going to be 29 over 2 times 2, which is just 29 units squared. And there we are. That is my answer. That's the exact area of the rhombus. So there. Okay. Cool. So yeah, so that's it for this section. So hopefully you've seen how we can tackle the various types of geometric problems with vectors. So yeah, so I'll see you next time.